Alright, so this is going to be a video on 9.3, which is about inferences about two sample means for independent samples. So the keyword there, independent, is going to come into play here real quick. So basically, this is comparing the averages of two different populations. So, you have, again, two different cities or two different states, we'll say, is this state on average taller than this state, so on. So, first thing to talk about this independent and dependent business. So independent is when you're taking two sample populations, two sample value selections, where one population and the other are not related. So the previous example there, two cities, right? If you take people from city A and take people from city B, those are independent. They have no connection to each other at all. Dependent is the opposite. Dependent is when members of one sample can be connected or to determine the members of the other sample, or sometimes called matched pairs. This is basically like, well, I have an example here. Let me not try to go this here. So just to let you know here, the ones we're going to be working with today are the independent samples, where we're going to have both samples have no connection to each other at all. Okay? And again, this is normal rules apply as before. But what we're talking about there versus independent or dependent. This is an example of the independent one, the Rogaine thing. The effectiveness of excuse me, the top one here, the effectiveness of Rogaine is tested by comparing results of balding men before and after treatment. This is actually, sorry, I misspoke here. This is actually an example of matched pairs because the people in sample 1, which are balding, are the same people in sample 2, which are after the treatment. So before and after is an indication of matched pairs. You're tracking the change from one group to the same group, but over a period of time after some sort of treatment is applied. The second example is one that we're going to work with today, which are independent, because you have one group that has one situation, and another group that has another situation. In this case, eye drops. One group has a prescription eye drop, one group has a placebo. There's no connection between them. They're both independent of each other, and we're going to compare their average results there. So again, the second example is going to be the ones we're working with today, the independent samples. Okay? Again, look for those keywords before and after. That's a matched pair keyword. Placebo is usually an indication of independent, because if you have a placebo group, that means you likely have a non-placebo group, and again, they're separate. So hypothesis testing for a two mean. This is our test stat formula. Once again, you don't need to memorize this, nor do you really need to even use it. Give me a second here. Just doing a quick mic check. Okay, good. You don't even really need to use it. You simply need to use your calculator, which is this down here. So just to show you where this menu is, we go to stat, test like before, and then we're going to go down to the Samp T Test, because we have two samples and we're doing a T test because we're testing an average. That's the name, Samp T Test, right? We do not, I'll show you here, but there's going to be an option where it says pooled or not. We are going to choose no for pooled. So we're always going to choose no for pooled. And to find our critical value, in case we need to, we're going to need to know degrees of freedom. But in this case, since we have two samples, how do we know what our degrees of freedom is? Because our n for one sample might be different than our n for another sample. Well, we simply use a smaller n. So the smaller the two values is going to be our degrees of freedom. So whether it's the first sample n minus 1 or the second sample n minus 1, whichever one's smaller, those are my target degrees of freedom. Let's do an example here. So we have a case in Ireland. I think this was an actual case too. I don't think I included all the data just to make this a little bit more time manageable here, but this was data taken from a case where you have age of successful applicants and age of unsuccessful applicants for a promotion test. And the claim here, the issue here is there discrimination based on age? Is this test geared more towards younger folk than it is towards older folk? Well, basically what we're going to ask there then is there a difference in the average age? Is the average age of the unsuccessful group any different than the average age of the successful group? Or put another way, is the average age here, AVG, is this average age higher than this average age, right? If we want to figure out, are these people generally older than these people, we want to figure out if their average is higher than these, right? And it seems like that might be the case here. I mean, you have a 27-year-old here, and there's no 20s here at all. The lowest we have is, what, 34? Here we have the highest is 51. Here the highest is 60. So it looks like it might be the case, but we don't know for sure because there's a fair bit of overlap as well. So that's what we're going to try to find out. Is this, if you took this to court, and I believe this was actually taken to whatever Ireland's court is there enough evidence to show that this is the case? So what we need to do is we need to list out our stuff here. So I'm going to go to the next slide here so I can actually write on some stuff here. So if you need to go back and forth to memorize the numbers here, that's fine, but I will give you the necessary information over here. So we first need to write our hypotheses, right? So my H, well, that did not go as well at all. Jeez, that's really on force today. HO and H1, man, if I draw a big H here, if that's going to bother anything. There it goes a little bit. Okay, sorry about that. Again, I don't know why this is getting worse and worse, it seems. So, HO, come on. My hypotheses for HO is going to be that the averages are equal, right? That's my first hypothesis, that there's no age discrimination. Everything's just equal. All the averages are just fine. Wow, this is just like massive there. Definitely going to need to erase that. My alternative then is not that the averages are equal, obviously, because that's my hypothesis for the original. My alternative is that the averages are not different, but specifically that the average of group 1 is bigger than the average of group 2. So when you're doing a tail test, when you're doing 2 samples, you have to really make sure you get that alternative one right, because it can be very easy to flip your groups accidentally. So make sure you determine yourself first which one is group 1 and which one is group 2. In this case, we want to test if the unsuccessful applicants have a higher average age than the successful applicants. And this is my claim right here. This is my little c. So I need my test stat, I need my PV, and I need my CV. Right. Now again, technically you don't really need your CV and your PV. You just need one of the two because you can compare just fine as long as you have one of the two. But we're going to get both anyway, and I have to redraw my P now. And remember, we're doing an alpha of 0.05. I think they wrote that there. If not, they should have, but it's a 0.05 significance. Okay. So, like I said, we shouldn't have to do much work here. We're just going to mainly serve as a vessel of entering the stuff into the calculator and then interpret the results that come from that. So let's go ahead and get to my calculator here. Now, you can either find the averages yourself or you can enter them as a list. So, for example, if we go to this 2 Samp T test, it gives us two options. It says stats or data. Stats or data. Stats or data. Stats. So if we go to stats, that means you already know all the statistics. You already know what the average is. You already know what the standard deviation is of all the groups. And if you do, great, you can use that. If you don't know what these are, you can find them out. Or you can go to this data section here. The data section says, okay, you give me the lists, and I will get all that information for us. So in order to use this, you first have to actually make your list. So if we go to edit here, I believe I entered these in already. Let me just double check my numbers here. So I went to my list, and I entered in all this information ahead of time. So I entered in all the information for the first applicants in list 1, all the information for the second applicants in list 2. Then go stat, test, to Samp T, and then I can just click the data section and make sure that my first group is list 1, my second group is list 2, frequencies should still be 1, that's fine. Make sure I click the right hypothesis, right? So I want to test to see if my unsuccessful group is higher average than my successful group. Always choose no for pooled, and we want to calculate. And there's my information. So again, you can do it either way. It just depends on what type of data you're given. But usually, if they don't give you the information directly, you can just enter in the list yourself and have the computer or have the calculator do all the heavy lifting. So my t-score in this case is 1.39, my p-value is 0.087, and my CV I had to figure out actually. So my t-score is 1.39. My p-value, if I go back here, is 0.087. 0.087. Now my CV you do need to actually look up. You don't have really a choice for your CV there. So you're going to have to use your t-score table and look up your critical value for 0.05 significance. If we go back here, I believe of the two lists I have, the smaller list is 16, right? My first list. So there's 16 values in my first list, so my degrees of freedom is going to be 15. So I have 15 degrees of freedom. So my degrees of freedom is 15. And so what that means, I'm going to look at my t-score table. It's a one-tail test, so I'm going to go to the one-tail column, look where 0.05 is. Whoops. Try again. I hate that I have to double-click that. It's really annoying too. There's a bunch of things on PowerPoint that annoys me, but it's the best tool I have right now. So here's 0.05. Go down here to find where 15 is and find out what my critical value is on my t-score table. In this case, it will give you a t-score of 1.755, and that would be my critical value for this situation. And then I compare. Now, once again, you can compare it using the critical value or the t-score. I prefer to use the p-value, so we're going to use that. So we put 0.087 and compare it to 0.05, and it looks like we're going to fail to reject because 0.08 is just enough above 0.05, about 3.7% more than what we need. And so this does not, whoops, does not support my claim. My claim that there is an age difference on average between people who failed and people who succeeded at the promotion is not supported by this evidence. Now, here's the thing though. It was a very close not support, right? So this might call into suspicion here. Like again, you had 0.87 versus 0.05. This might call into suspicion things like, okay, well, maybe there is. We just didn't necessarily have quite enough evidence there. And in fact, this case, I believe, if I remember correctly, was actually determined to be discriminatory against age because what they did is they came up with another study that said, okay, instead of testing to see what average greater, let's test to see if the first case, or the two cases of the two applicants, if there was a higher amount of people over 50 for the first case than there was for the successful case. So instead of saying, is the unsuccessful cases higher age on average than the successful cases, they said, is there more people over 50 in the unsuccessful area than there is in the successful area? So that's another thing with statistics, that you can play around with what question you ask and what you're looking for. Because if you're saying, is there age discrimination? Both of those things are valid, no. Is there age discrimination? Well, I'm going to check the average age and see which one's higher, if there is. Or is there age discrimination? Well, I'm going to see what group has more people over 50 and then see based on that. So again, depending on how you ask and what you're looking for, you can, again, that's what they say, you can lie with statistics in a very sneaky way depending on how you use it, but hopefully as you know statistics, you can prevent yourself from falling for those lies as well. All right, so let's try another one here. A study is conducted testing the effects of marijuana use on mental abilities. In this case, we're using a 0.01 significance, so just FYI there. And we're going to test the claim that the heavy users have a lower mean on this cognitive test than light users of marijuana. All right, well, let's make our hypothesis here. So HO and H1. Okay, so HO says the average are equal, right? HO is always going to be averages are equal, and H1 is going to be that the light users, we'll call this group. Actually, you know what? It might be easier just to call the heavy users group 1. So why don't you do that way? We'll call the heavy users group 1, and we'll call the light users group 2. That way we can do a right tail test again. Because, like I said, if you're using a t-score table, right? This is a t-score test. Right tail tests are generally easier to comprehend and work with than left tail tests, right? So let's just do a right tail one. So is bigger than the second group, right? Oh, wait, no, sorry. Have a lower average score. My bad, I did that wrong. My apologies. So if it has a lower average, then we should keep it as it is then. So we should say that this is group 1, my bad, and this is group 2. So group 1's average is higher than groups 2 average, right? The light users have a higher average than the heavy users because we want to see if the heavy users have a lower average than the light. So I set this up correctly here in terms of the orientation, my bad. So remember, this is light users, this is heavy users, put a little marking there. And again, this is going to be my claim, right? Is there a difference in favor towards the light users of marijuana compared to the heavy users? Well, let's go ahead and get our stuff here. We need our t-score, our p-value, and our critical value. And again, we're going to go to our calculator to do that with. Now, in this case, we don't have the raw data, right? We don't have the actual lists of values. So we're going to go to the same item, but in this time, we're going to enter it in under stats because we have the raw stats with us here. We don't have the raw data, but we do have the raw stats. So group 1 here, we had, let's see here. We had X bar 1. So that's 53.3. Sorry, I blanked there. My average for the first group is 53.3. My standard deviation for the first group is 3.6. My total number of people in the first group is 64. And the same thing for the second group, 51.3 average, 4.5 standard deviation, and 65 number of people. And I'm testing to see if group 1 is bigger than group 2. So okay, that's right. Don't want to be pooled. Go ahead and calculate. So 2.79 we'll say is my t-score. 2.79. My p-value was 0.003, I believe, right? 0.003, right? So p-value is right here, 0.003. And then, hold on here. That's weird. Let me make sure I entered in the right one there. Samp T Test. -65. No pooled. Okay. All right. So I'm not sure why they gave me the degrees of freedom there as 121. So again, I'm not sure why the calculator popped up that, but usually doesn't do that. But oh well. But these values are correct so far. So to find my critical value, then once again, I'm going to be using the 0.01 column this time. That's my alpha now because I'm doing a little bit more of a tougher significance here, 1% rather than 5%. And so then if I look that up in my t-score table, my degrees of freedom wouldn't be 121. Again, don't trust your calculator on that. My degrees of freedom in this case would be 63 because that's one less than my lowest value, my lowest n here, which is 64. So one less than your lowest n is your degrees of freedom. So you look that up on the t-score table. Once again, you can look back and see how to read a t-score table for that if you want to. But this critical value should end up being 2.39 when I checked it. If I'm wrong, please let me know. But I've checked it twice now, and I believe it's 2.39. And anyway, we're going to go ahead and compare the p-value portion of this no matter what. So 0.003 is less than 0.01. So even with this higher bar here, even with this higher significance, or I should say lower significance level, but this higher test for significance here, we would still reject reject HO, and we would support our claim. Support our claim. So it does seem like there is enough evidence in this situation, at least, to say that the light users have a higher average score on a cognitive test than heavy users of marijuana. Now, it'd be interesting to see if we can put these up against no users of heavy marijuana. Because again, if we have no users versus light users versus heavy users, that gives us a little bit more pantogramship. But this does seem to play into the idea that marijuana use does have a lowering effect on mental ability based on this study. Now again, stats doesn't say whether something's true or false, but that seems to be what the implication here is for this data. Now again, make sure that we have two different kinds of tests we talked about now between this video and the last video. We have a two test for proportions and a two test for averages. So if you're testing a claim about a proportion or a percent of the population, you're going to be using a z-test. If you're testing a claim about an average, you're going to be using a t-test. That's that two prop z, right? This is two prop z. This is two samp t. Those are the two menu items you want to click on in your calculator depending on what you're working with here. So let me give you an example here. Willy Wonka wants to test to see if the average weight of M&M's packs produced between two different machines are the same. The data produced given below. Do the machines appear to have the same average weight? Well, in this case here, we're testing to see if the machines have an average weight difference, right? This is this is an average estimate, right? We're testing an average, not a percentage. So this is going to be a 2 Samp T test. We're testing an average, so we just did in the past examples, we use our 2 Samp T test. So again, if you enter in this data in your 2 Samp T, I'll just go ahead and do that here real quick, just to test this real fast. So again, we're doing 2 Samp T because it's an average test. We're going to go to stats because we just have the raw stats. This is, sorry, 3.05. 05. That's our average weight for the first pack of M&Ms from this machine. We have standard deviation of 1.2 and an N of 30. And over here, my average weight was 3.19, standard deviation of 1.8, packs of 30. It says that we're testing to see if two different machines are the same, if they produce the same amount of M&M packs, the same quality. So my HO is that the averages are the same, which is actually my claim as well, right? I'm claiming that everything's the same. So this is my claim. And then my H1 is that the averages are not the same, right? So if I go here, I want to make sure that I click the right claim, or not my right claim. I want to click the right alternative, which is this one right here, that they're not equal. And then calculate it. P-value of 0.724. I won't bother with the test stat right now, just to speed up the length of this video here. So 0.724 is my p-value. That's my PV, 4. And so I can compare that to my alpha. And my p-value's already been doubled. All that my calculator will take care of all the doubling and whatnot, so you don't have to worry about doubling it again or subtracting by 1. Your calculator does all that for you. All you need to do now is compare this p-value to your alpha, which is definitely a lot larger than your alpha, right? 72% versus 5%. So this would be a fail to reject. I'll put FTR here. Fail to reject HO. And then we're going to support our claim. And the reason we're supporting our claim is because, once again, we claim that they were equal, the averages. This data seems to suggest that they are equal, so we support our claim. Support. Right? So that one was a testing an average. This one here, which might sound similar, is a little bit different. This says that you're testing to see if the proportion of packs at this East factory matches the proportion of quality packs at the West factory. So we have two different factories producing M&Ms, M&M packages, we should say, and we want to make sure that each package meets quality standards for both factories. So we're testing a proportion or a percent. Now we're testing how much percentage of these packs at this East factory match the quality of the percent of packs from the West factory. So we have East and West. We'll put E and W. For the East, they got 112 boxes, and they found that 8 of them did not meet regulations. So we'll say that 8 is here. Again, we're testing to see if they meet regulations, but we'll kind of test for the no meet stuff and then kind of use our interpretation for that. So, God, I hate those lines. So we're going to test to see how many unquality packs there are and see if that's the same, right? Because if they have the same amount of defects, then obviously they're probably the same amount of successes as well. So 112 packs, 8 of them didn't match standards. At the West factory, they tested 98 packs, and 5 of them did not meet standards, right? So we want to figure out, are these two factories rather, producing the same amount of quality packs based on how many packs they got rejected under a quality inspection here. So since we're testing a proportion, we're going to be using a 2-Samp Z test, right? Or 2-Prop Z test, as the case may be. So we're going to go to our calculator, and this time we're going to go to 2-Prop Z. Whoops. Where is this? Oh, I was there. Sorry. 2-Prop Z test. I saw the T in test. I thought it was a T test. And we're going to enter in our information there. So we have 8 out of 112 for the first factory and 5 out of 98 for the second factory. We should probably write our hypotheses here. So my HO, once again, is that the P's are equal. My H1 is that they're not equal, because I want to see if they have the same quality in each factory. See, no problem there. So we want to test to see if they're not equal or equal. We get a p-value of 0.5403. So we'll say 0.54. So my p-value here is 0.54. So 0.54 is less than 0.05. Not sure why I keep getting random marks there now. So 0.54 is less than 0.05, so we know that if the p-value is low, or sorry, my bad, I said that completely wrong. 0.54 is bigger than 0.05. Some of you probably yelling at me again. So since my p-value is high, we're going to fail to reject my HO. And my claim was that both factories have the same accuracy. Well, this says that they both have the same number of defects. They both have the same number of packs that didn't meet specifications, which by extension means they both have the same number of packs that meet specifications as well, right, in terms of proportion. So we would say that this does support our claim. It does appear that these two factories have the same proportion of defects and quality M&M packages that they produce, right? So again, read your problems carefully so you know what type of test you're doing, because they're both going to have 2 samples and they both might sound very similar, but you're looking for keywords like proportion, average, and percent. Proportion and percent is a Z test, average is a T test. Hope this video helped you out. Sorry for the length. Have a good day.